Hi students, today we're going to study about the combination of capacitors. Let's say you have one capacitor like this, and then you attach another capacitor like this to the first capacitor, and then you attach yet another capacitor like this to these two capacitors. In that case, what will be the final capacitance of the entire system? So what will be the effect, of all these three capacitances? What will be the one final capacitance that can replace all these capacitors? That is what we are going to study in combination of capacitors. So let's begin our study. Now before we study about exactly what happens when two or more capacitors are joined together, let's first understand certain basic concepts. The first concept is that a capacitor stores energy, not charge. You see, the left plate of the capacitor here has a charge plus Q, and the right place of the capacitor here has a charge minus Q. But the net charge, enclosed by the capacitor is 0, isn't it? And therefore, you can say that the capacitor does not really store charge because the net charge stored by the capacitor is always 0. However, there's always some energy in between the capacitor plates. This yellow energy here. We say that the energy is half CV square. So this energy is what is always stored in the capacitor plates. So you must remember that the capacitor is an energy storing device, not exactly a charge storing device. This energy stored between the capacitor plates is the potential energy of the capacitor. It is also equal to the energy stored in the electric field of the capacitor. Understood? Let's move on to the next concept. The next concept is the equivalent charge on a network. Well, if you have capacitors like this and a battery connected to the three capacitors like this, in that case, the equivalent charge on the network is the sum of the charges on all the plates connected to the positive terminal of the battery. So let's say our capacitors are connected like this, and here's a battery. In that case, if this plate has a charge plus Q and if this plate has a charge minus Q, in that case the equivalent charge on the network will be plus Q because the plate connected to the battery has a charge plus Q, isn't it? Now this equivalent charge on the network physically represents the net charge that the battery is extracting from one plate and transferring to the other plate. For example, the battery here is extracting a charge Q from all these three plates and it's transferring that charge Q to all these three plates. So the net charge transferred by the battery is basically the equivalent charge on a network. The next concept we're going to study is the concept of island law. The island law states that the charge on the isolated part of any circuit is always conserved. Now this seems to be such a complicated statement. What's happening in this statement? But basically, the island law states what you and me already know perfectly well. It states that if any part of a circuit is not connected to the other parts of the circuit, in that case the charge on that part of the circuit will remain constant. So for example, if you take two capacitor plates and the left capacitor plate has a charge plus Q and the right capacitor plate has a charge minus Q, and if you don't connect these two capacitor plates to any circuit, the circuit itself consists of these two capacitor plates. They're not connected to any battery, they're not connected to each other, nothing. In that case, the charge on these two capacitor plates will remain constant. The plate on the left will always have a charge plus Q. After all, where will the charge plus Q go if this capacitor is isolated? Isn't it? Similarly, the charge on the right plate will always be minus Q. Similarly, if you take any object here which has a charge plus Q on it, in that case the charge on this object will be constant. That's because nothing is connected to this object. So where will the charge on this object go? On the other hand, if you earth the object, in that case there is a chance that the charge on the object might change. That is because to make sure that the potential of this object is 0, the charge on the object may vary. And again, if you remove the earthing, the final charge on the object will again be constant. So for example, if you take two capacitor plates like this, the charge on these two capacitor plates will be constant, plus Q and minus Q. However, if we connect these two capacitor plates to a battery like this, in that case, the charge may or may not be constant. For example, if you increase the distance between the capacitor plates, like this. In that case, since the capacitance is epsilon naught A by D, the capacitance will decrease, and so the charge on the objects will also decrease. However, if you bring the plates closer, the charge on the objects will increase. So the point is, if a battery is connected, there is a chance that the charge on the capacitor plates might increase or decrease when you change the capacitance of the circuit. But if there was no battery, if there were only those two capacitor plates and there was this charge stored in the capacitor plates, in that case you could take the capacitor plates away from each other, you could bring them closer, you could increase their area, you could do whatever, but the charge on the capacitor plates would be constant. So the island law basically states what we all know, that the charge on an isolated body or an isolated part of the circuit will be constant. Understood? Now let's finally come to the point where we study what happens when we connect different capacitors together. The first type of connection in which we can connect different capacitors together is the series connection. When do we say that capacitors have been connected in series? We say that capacitors are in series when they are connected one after the other, after the other, after the other with respect to the battery. So for example, if you say that this is the positive terminal of the battery, then capacitor C1 is connected to the positive terminal of the battery, capacitor C2 is connected to capacitor C1, capacitor C3 is connected to capacitor C2, and then finally the last plate of capacitor C3 is connected to the negative terminal of the battery. So whenever capacitors are connected one after the other, as you see in the figure, they are said to be in series. Now one fascinating fact about a series connection is that the charge on each capacitor in a series connection is the same. So capacitor C1 will also have a charge plus Q and minus Q on its plates, capacitor C2 will also have a charge plus Q and minus Q on its plates, and capacitor C3 will also have the same charge on its plates. Now this is a fact you must remember, but then why does this happen? Well, let's derive that. You see, when we connect this battery to all these three capacitors in series, in that case charges plus Q and minus Q appear on the ends of the capacitors connected to the battery. So for example, this plate here and this plate here, this one, both of them are connected to the battery, isn't it? So this plate will acquire a charge plus Q and this plate will acquire a charge minus Q, because the battery will transfer a charge Q from this plate to this plate, isn't it? So this plate will acquire a positive charge and this one will acquire a negative charge. Now minus Q and plus Q charges will be induced on the plates which are just next to the extreme plates. So for example, this plate and this plate are the plates connected to the battery. We just saw that these plates acquired a charge plus Q and minus Q. Now if this plate acquires a charge plus Q, this plate will acquire a charge minus Q, an induced charge minus Q, because of Gauss's law. And if this plate acquires a charge minus Q, this plate will acquire a charge plus Q because of Gauss's law. You see, you can take a Gaussian surface like this, a cuboidal Gaussian surface. And as we had derived in the earlier chapters also, the net electric flux passing through this Gaussian surface will be zero, isn't it? Because the electric field will be in this direction. Therefore, the electric flux will pass through only this surface and this surface. But we know that the electric field passing through a conductor is zero, and therefore the net electric flux also passing through this entire area will be zero. And so, since the net flux is zero, the net charge enclosed will also be zero. So basically the net charge enclosed by two conducting plates placed before each other is zero. So if there's a charge plus Q on this plate, then there has to be a charge minus Q on the other plate, according to Gauss's law. And therefore this plate here and this plate here will acquire equal and opposite charges, isn't it? So what about the middle plates? Like, why will they acquire a charge plus Q and minus Q? Well, that is simple too. You see, these two systems here are islands with net charge 0. For example, just consider this plate, this wire and this plate. Isn't that an isolated island? It's not connected to any other circuit. It's absolutely, isolated, like there's air on each side of this circuit, isn't it? Similarly, this part of the circuit, isn't it an island? It's not connected to any other part of the circuit. There's this plate and this wire, that's it. And that means that the net charge on this island will be constant. So if there's a charge minus q induced on this plate, then a charge plus q must be induced on this plate to counter the charge minus q, because both these plates constitute an island. Similarly, if this charge plus q is induced on this left plate, in that case a charge minus q must be induced on this plate here, because this entire system is an island, isn't it? And so that is the reason there will be a plus q charge and a minus q charge in the middle plates. And that is the reason why the charge on all the capacitors in a series circuit is the same. Here we go, plus q minus q plus q minus q and plus q minus q. The potential difference across each capacitor in a series circuit, however, is not the same. You see, if you carefully consider the potential drop across each capacitor, if the potential drop across the first capacitor is V1, the potential drop across the second capacitor is V2, and the potential drop across the third capacitor is V3, in that case, V1 plus V2 plus V3 is equal to V. So in a series circuit, the net potential drop, across all the capacitors is equal to the sum of the individual potential drops across each capacitor. Understood? And that has to be so, because you see, if there's a potential difference V created by the battery, then the sum of all the potential differences must be equal to the potential difference of the battery. So these are the 2 points that you must remember in a series circuit. The potential difference is the sum of the net potential differences across each capacitor, and the charge on each capacitor is just the same. Now when you equate the sum of all the potential differences to the net potential difference created by the battery, you can actually write Q by C is Q by C1 plus Q by C2 plus Q by C3. That's because the net potential drop across each capacitor is Q by C. So for example, the potential drop across capacitor C1 is Q by C1, and the potential drop across capacitor C2 is Q by C2. So when you equate Q by C to Q by C1 plus Q by C2 plus Q by C3, Q gets cancelled off because the charge on each capacitor is the same. And that gives us the final expression 1 by C. The net equivalent capacitance of a series circuit is such that 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So in a series circuit, if C is the equivalent capacitance of the series circuit, in that case 1 by C will be equal to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. So what you can say is that instead of these capacitors C1, C2 and C3, you can basically use a capacitor C like this to replace all these 3 capacitors. In that case, this capacitor C will have the same charge as all these 3 capacitors, and it will have a potential difference V across it. So you can replace these 3 capacitors by this single capacitance such that this formula is valid. Of course, you have to remember this expression for the equivalent capacitance in a series circuit. It will be used again and again in so many objective type questions. What happens when there are 2 capacitors in series? Well, the situation is obviously much simpler. In this case, you can equate the charge present on the 2 capacitors, Q1 equal to Q2. And when we do that, we get C1 V1 is C2 V2, because the charge stored on any capacitor is CV. If we also use the equation V1 plus V2 is V, and we try to find out the value of V1 and V2 in terms of V, in that case we get these 2 expressions. V1 is C2 by C1 plus C2 into V, and V2 is C1 by C1 plus C2 into V. Understood? So basically the potential difference is also in the inverse ratio of capacitances. As you can see, V1 by V2 is C2 by C1. So you must remember this point also, that the potential difference ratios across each capacitor in a series circuit is proportional to the inverse of the ratio of the capacitances. Understood? Now let's study about circuits in parallel. Well, just as we had a series circuit in which capacitors were connected one after the other, and then connected to a battery, in a parallel circuit, the capacitors are not connected one after the other. In this case, they are connected in such a way that all the capacitors have one terminal connected to the positive end of the battery, and all these capacitors have the other terminal, the negative terminal, connected to the negative end of the battery. Understood? So for example, if you have these three capacitors here, what you can see is that this positive terminal of the battery is connected to one plate of each of the capacitors. The negative terminal of the battery is connected to the second plate of each of the capacitors. So when this happens, in that case the capacitance are said to be in parallel. As you see, in the case of a series circuit, only two plates are connected to the battery. The plates at the ends are connected to the positive and negative terminals of the battery. But in case of a parallel circuit, all the capacitors are connected to the battery directly. In the case of a parallel circuit, the potential difference is the same across all the capacitors. And this is obvious too. That's because, if you look at this capacitor C1, in that case, both the terminals of the capacitor are connected to the positive and negative terminals of the battery. So the potential difference across this capacitor must be C1. Similarly, in the case of the second capacitor, both the plates are connected to the positive and negative terminal of the battery. So again, the potential difference across the second capacitor must also be equal to V. And similarly, even in the case of the third capacitor, one plate is connected to the positive end of the battery and the other plate is connected to the negative end of the battery. So the potential difference must again be V. In this case, how do we calculate the equivalent capacitance of the circuit? You see, in a parallel circuit, when the potential difference across all capacitors is the same, but the charge is not the same. Well, if you consider an equivalent capacitor like this, in that case, this equivalent capacitor will have the same potential difference as the battery, isn't it? And what charge will this equivalent capacitor have? The equivalent capacitor plates will have net charge imparted by the battery to all these three capacitors, isn't it? So the battery is imparting a charge Q1 plus Q2 plus Q3 to all these three capacitors. So this equivalent capacitor will have a charge Q and minus Q such that Q is equal to Q1 plus Q2 plus Q3, because that is the net charge that the battery is transferring from all the negative ends of the capacitor plates towards positive ends of the capacitor plates. So when we say that Q is Q1 plus Q2 plus Q3, we can say that the CV is C1V plus C2V plus C3V. CV here represents the net charge transferred by the battery, and C represents the equivalent capacitance that can replace all these three capacitors. So as you can see, V cancels off from all these expressions because V is the same for all the capacitors. And that gives us the expression that you must remember. The equivalent capacitance in case of a parallel circuit is C equal to C1 plus C2 plus C3. So the equivalent capacitor that can replace all the capacitors connected in parallel is basically the sum of all the individual capacitances. Understood? Again, you must carefully remember this formula. So if I can repeat it to you, in case of a series circuit, 1 by C is 1 by C1 plus 1 by C2 plus 1 by C3. But in the case of a parallel connection of capacitors, C is equal to C1 plus C2 plus C3. That was about series and parallel connections. Initially you might find this a bit confusing, but we'll keep on solving some problems and that will simplify all the concepts. Let's start off by solving this problem here. Calculate the capacitance of two square plates of sides A placed as a slightly open book at a small angle theta. The two nearest parallel edges are at a distance d as shown in the figure. So what is happening in this question? You see a green plate in this figure and it is at an angle theta with the horizontal and also with the second plate. We have to calculate the net capacitance of these two plates. This capacitor that you see on your screen. How do we calculate the capacitance of this instruction that you see? Also, what has this question got to do with series and parallel combinations? Well, let's study this question a bit more carefully and let's find out. You see, ordinarily, when we are given two plates facing each other, we just say that the capacitance is epsilon naught A by D, isn't it? Where D is the distance between the plates. In this case, however, the distance D between the plates is varying, isn't it? When the plates are placed parallel to each other, the distance is constant. In this case, the distance is d here, it's something else here, and it's absolutely something else here, isn't it? We cannot just say that the net capacitance here is epsilon naught A by D. What we will have to do is, we will have to consider any particular element on both these plates. Like we'll consider an element here on this plate, and we'll consider an element here on this plate, and then we'll have to calculate the capacitance of the capacitor consisting of these two elemental strips. So if we consider an elemental strip like this and an elemental strip like this on either of the plates, then first we will calculate the capacitance of the element CE, and then using the capacitance of the elements, we can find out the net capacitance of this entire system. So suppose we take an elemental strip like this here on the green plate, and we take an elemental strip here on the brown plate, a corresponding elemental strip. And now if we keep on taking such combinations of elemental strips, like we take an elemental strip here and a corresponding elemental strip here, and suppose we take an elemental strip here and we take a corresponding elemental strip here, in that case what you can see is that all these baby capacitances or all these mini capacitances of the elemental strips are in parallel. Fascinating, isn't it? You see, when we connect a battery across this capacitance, we'll connect it like this, isn't it? The positive end here, the negative end here. And as you can see, for all the mini capacitances that we take throughout the length of these two plates, the net potential difference because of the battery will be the same. So we can actually replace this two plate system by this figure. We can replace it like this, by a huge number of mini capacitances, all of which have the same potential and which are connected to a battery, isn't it? Like all the strips that we took here are all these mini capacitances. Understood? So basically, if we calculate the capacitance of two elemental strips considered randomly on these two plates, in that case all the capacitances that we consider on these two plates will be in parallel. Now we know that in case of parallel connections, the equivalent capacitance C is C1 plus C2 plus C3 and so on. So in this case, if we take all these elemental capacitances or all these capacitances of the elemental strips, in that case we can directly add up all these capacitances, and the sum of all these mini capacitances will be equal to the net capacitance of this two plate system, isn't it? I know it's slightly difficult to grasp, but the core concept that I'm going to hint at is that we are considering small strips on both these plates as mini capacitances, and we are trying to calculate this mini capacitance. Then we are trying to add all these elemental capacitances to get the final capacitance of this two plate system, since all the small capacitances are in parallel, isn't it? So for example, if the capacitance of a certain two strip system that we take is CE, in that case the net capacitance will be CE1 plus CE2 plus CE3 plus CE4, where CE represents the capacitance of any two elemental strips that we take, isn't it? Because all these mini capacitances are in parallel. Now we are taking very very thin strips, so thin that we can say that the length of the strip is dx. Like if we consider a distance x from one end of this plate, in that case the width of both the strips is dx, the strip on the green plate and the strip on the brown plate. So what you can see is that there will be infinite such strips throughout the length of these two plates, isn't it? And since there will be infinite such strips, we can basically say that C is the integration of the elemental capacitances, isn't it? So when we try to depict all this mathematically, this is what we get. As you can see, x is the distance of the elemental strip from the origin. Capacitance between the elemental strips is this expression, epsilon naught a dx by d plus x theta. Now how did that come from? You see, if you consider only these two strips, the strip on the green plate and the strip on the brown plate, in that case the capacitance of that two strip system will be epsilon naught into area of each strip, that is dA, divided by the distance between the strips, isn't it? Now the area of each strip is clearly A into dx, because the width of each strip is approximately dx and this length is A, isn't it? The side of the plates. So dA is A dx. The distance between the strips is clearly d plus x tan theta, isn't it? After all, this distance here is clearly x tan theta and this distance here is d. Now we know that for small angles of theta, tan theta can be approximately written as theta. And we are given in the question that theta is a very small angle. So I have replaced tan theta by theta here. So that is how, the distance has become d plus x theta, and how, the area of each strip has become a dx. So when we try to integrate and find out the final capacitance of the entire two-plate system, we integrate from 0 to a, that is from x equal to 0 to x equal to a. And that gives us the value of the final capacitance of this two-plate system as epsilon naught a by theta ln 1 plus a theta by d. And that is our final answer. The main problem that we faced in solving this question was that the distance between the two plates was not constant. So we took two elemental strips for which the distance between the strips was equal to a fixed value d plus x tan theta, and then we integrated this elemental capacitance across the entire two-plate system to calculate the final capacitance of the two-plate system. We could integrate because the capacitances of the elements were in parallel, and in parallel you can add up all the capacitances. So this problem was basically slightly on the tougher side, but then if you can carefully grasp it, think about it and understand it, I am sure you'll be able to directly solve most of the series and parallel problems asked in IIT JEE. Understood? Let's now move on to the next concept,